Hello, this is Manoj, and today I'm going to tell you a little bit about a human machine interface which has gone faulty. Basically, the board which you are seeing in front of you, this is an HMI or a human machine interface. In other words, it basically is a small computer board with a display which can display the data of various industrial process, and it can also issue commands for their control through touchscreen LCD. So basically this is an industrial computer with an LCD display, which you can see here. This is an LCD display and which is being controlled by this board. The upper portion of the board you can see here, these are the computer circuits, and you have all the various USB controllers. You have here RS485, RS422 ports. You can see the BIOS battery. These are the USB ports, and at the lower side of the board you can see the various controllers, chips and ICs, capacitors, etc. The cost of this board is around 7 lakhs. So it has gone faulty due to a lightning strike. It may be a lightning strike. So I just thought we'll just take it apart and see what all are there, the components inside, and so you can study it a bit. So the purpose of this video is to explain the various voltage regulators and the LCD backlight drivers in this HMI. So you take any laptop board or any computer board, you'll have a lot of regulators inside. These regulators, they convert one voltage from one level to another. So I will just see in the lower part of the board, you can see this is the input power supply. This is a 24 volt power supply. This board takes a 24 volt input. This is presently it is being supplied by this power supply. It can give around 10 amps of power of current, and the 24 volt goes inside here. This blue color chip is called a MOV, or a metal oxide varistor, and it basically prevents the board from any damage due to any surge current or any lightning strikes, etc. But unfortunately, most probably it didn't do its job, or maybe it had done its job many times and it has failed, and so the board could not be protected from this particular surge and has gone faulty. And I will tell you where it has gone faulty, which chip has gone faulty. So presently you can see, like there are many regulators inside this. This is one particular regulator. This is another regulator, and this is the display controller. This is what has gone faulty. This is what has gone faulty inside this board, and that is why the display is not showing. Here you have another regulator. This also it gives around 3.3 volt DC. 3.3 volt DC it gives for the upper board. So basically here you have the 24 volt DC coming in. This 24 volt DC comes in through these filters. You can see these are the line filters. You can see they are like inductors. Two inductors are there, and both the positive and negative are looped through concentric inductors, and they are done like that so that any common mode noise in both the plus line and the minus line goes off, is cancels out, and you get a clean power to the board. These two MOSFETs are switching MOSFETs. They couple the 24 volt power supply to the board. If for any reason, if the main computer detects that there is some issue with the power in the board, it just gives the disable signal to these MOSFETs. So this 24 volt supply will not go forward into the board. Fine. Now this 24 volt supply is also supplied to this particular regulator here. This regulator here. This is the main regulator, which it's a DC to DC converter. What it does is it converts the 24 volts into 5 volt. This 5 volt is used for driving other functions of the board. So basically all the integrated circuits, they don't operate on 24 volt or 12 volt like that. Most of them, they operate on voltages like 5 volt and 3.3 volt, etc. Why? That's a long history. Basically, the transistor logic, it started with 5 volt. So down the line, all the ICs and chips also started using that 5 volt. Later on, the ICs also started using a 3.3 volt supply. So here, once the 24 volt supply is converted by this particular regulator to 5 volt, and this 5 volt is again converted to 3.3 volt. You can see here, this particular portion is the 3.3 volt supply portion, and you can see here, this you can see is the 3.3 volt point. So here if you test it, you will get 3.3 volts. So this 3.3 volt, it goes into this part of the circuit. These are the computer CPU, memory, peripherals. You can see all the USB controllers, etc. are all driven by this 5 volt and 3.3 volt. So as I said, this particular 5 volt is converted by this particular converter, 24 volt to 5 volt. Now this 5 volt again goes to this particular part of the section here. You can see here, this particular part of this section. Here the 5 volt is converted to 12 volts. This 12 volts is used for the backlight controller IC. So down here you can see this particular IC. This particular IC is called the backlight controller, and this requires 12 volts to power up, and that 12 volt is provided by this particular section. Now what happened here is this backlight controller basically what does is every LCD panel like this, every LCD panel will have LEDs inside. These LEDs provide the backlight of the panel. So you have 4 strings of LEDs. One string will have many LEDs, and these LEDs are driven by the backlight controller. Okay, back to our problem of the display. Basically, first let me tell you a bit about the various connectors in this LCD display. The black wires which you see here, these wires, these are 8 in number. These are the wires which control the backlight LEDs. So since there are 8 wires, you will know that each LED has an anode and a cathode. So there are 4 wires for the anode and 4 wires for the cathode. And each wire drives, or rather a pair of 2 wires, they drive a string. A string is comprised of many LEDs which are connected in series. Take a moment to note the LEDs, the backlight LEDs, how they are arranged and how they are connected to this IC. You see, this is the IC TPS 61199. This is basically the same IC which you are seeing here. This is the IC, and you can take the data sheet of this IC from internet. Basically what I did is I just noted down the part number and Google searched it, and Google will give you the particular data sheet of this IC, and they have printed this data sheet from my reference. And you can see the LEDs here. You can see 1 2 3 4 5 6 7 8 LED strings are there, and 8 LED strings are powered up. This is the anode part, and this is the cathode part. You can see the cathode is connected to these pins IFB1, IFB2, IFB3, so on up to IFB8. So that means the IC will produce a high voltage here. You can see here the IC is producing around 60 volts. The 60 volts is being produced by this IC, and this is given to the LED strings connected like this. So all the anodes are connected together, and it is given 60 volts is given to it, and each individual string is syncing into each individual IFB port. So a blank display means these LEDs are not firing up. There is some problem in the IC which is preventing the LEDs from lighting up. Next, I will show you the data connector of this particular LCD panel. These wires you can see these particular two wires, two cables, and they are called the LVDS cable. LVDS stands for low voltage differential signaling. This particular cable is connected to the microprocessor board here, so that gives all the data to the cable, which has to be displayed in this particular panel. So as you know, to create colors you require red, green and blue. So supposing you have a display which is like specified as 1920 into 1080, the normal HD resolution. So that means in the screen will have 1920 multiplied by 3 vertical lines, each line for red, green and blue. So you have 1920 multiplied by 3 vertical lines and 1080 horizontal lines. So where these lines meet are all the pixel points. So your image is basically which of these pixel points are turned on or turned off. So as you know, like if you in the olden times, if you go and zoom into a newspaper, because the resolutions were not that high, if you go closer to the image, you could make out the dots of the image. Something like that is happening, but the pixel pitch is very high, very sharp. So you will not be able to make out the individual images, individual pixels, but that is the way which pixel is on or which pixel is off will overall determine the image on the panel. So your LCD panel is basically your backlight, that is these wires, these 8 wires, which is having 4 LED strings, and the LVDS, but the LVDS connector. So you will get the data from the LVDS, and backlight will be given by these wires. So the combination of both will give the will be the LCD panel. Now let me again go back to the data sheet of the backlight controller. All these data sheets, as I said earlier, are available on the net. Our main problem today is of this backlight controller only. Because of this backlight controller issue, no image is visible on the LCD screen. This particular IC has got 20 number of pins, and all the pins are having various functions, and I will be focusing on the major pins and major functions. So you can see here, this is the V-in pin. The V-in pin is the voltage input to the spin. As I told you before, the 12 volt, you can see here 12 volt pin, 12 volt is coming in. This 12 volt is supplied to this pin, and this 12 volt is generated by the regulator in this board. As I told, this 5 volt is getting converted here by this regulator to 12 volt, and this 12 volt travels all the way down here, and this C173 point, you can see this C173 point will give the 12 volt. If I put a multimeter here, I will get the 12 volt here. So that is a converted from the 5 volt supply. I will show you 12 volts here. One sec. I take the multimeter here and then I touch it to this particular point, C173. So there is this VDD pin. This VDD pin is the internal 5 volt regulator inside this IC. This regulator is called the LDO, or the low dropout regulator. The function of this VDD pin is to supply 5 volt to the internal functions of the IC. So why is it given outside then? If the pin is for the internal functions of the IC, why that pin is given out? It is given out because to see the working of the IC. Supposing you take a multimeter probe and touch on the VDD, if you are getting plus 5 volt, means you can know that the IC is working, at least the LDO is working fine. So now this is precisely the problem in our case. When I see the VDD in my case, I am not getting the 5 volt, and therefore nothing of the internal circuitry will be powered up. I can show you the output in the multimeter. I will take the multimeter probe and then touch in the VDD. You can see here, I will touch the VDD, and you can see I'm touching on the capacitor. This capacitor is nothing but which is connected to the VDD supply, and you can see nothing. The meter is reading 0, no voltage at all. Okay, so since there is no VDD, the IC is useless, and therefore just because of this particular issue, this entire board, which is entire HMI, which is worth around 7 lakh rupees, is going completely useless. Next, I will come to another pin, which is the pin number 5, which is the enable pin. The enable pin, as you can see, input is coming from the board. So only when the input comes, input voltage of around 2.7 volts, if 2.7 volt reaches this enable pin, then only this IC will be enabled and it will produce any output. So even now, because of the fault here, even though enable pin is there, still the IC is not producing any output. But function wise, this is the thing. So whenever you want to turn off your laptop or go into the power save mode, etc., this enable pin is what it does. So if your computer is getting powered, if your computer is like going into hibernate mode or sleep mode, everything is controlled by this enable pin. The board just has to remove the enable signal, and the LCD will not consume any power. Okay, now I will tell about the enabled signal. You can see this is the enable EN pin number 5. This particular point is coming from the system board. So only when the microprocessor gives the enabled signal is this IC enabled. Now this has a very important function. Whenever you want to put your laptop into sleep or hibernate mode, etc., the microprocessor just withdraws its pleasure. It does not give the enable signal to this particular IC, and once the enable signal is not there, all the outputs will get disabled and your LCD will get powered off. That's why it can save the power, etc. And we can see where this enable signal is there on the board. I will show you. Only when you get the 2.7 volts from the board is this IC enabled. So here I have connected I have touched the point of the IC, the pin number 5, where the enable signal is coming. You can see I have touched it near to a small resistor. This is the enable resistor which is coming. The other side of the resistor is the signal is coming from the board, and I will show you the reading on the meter. This is 2.7 volts. That means the IC is enabled. Also, just see this small board here on the panel. This is the control board. You can see it is fed by a small ribbon cable, a white color ribbon cable, and this ribbon cable gives all the control signals to the board. So the microprocessor gives all the control signals to this board, Only when the LED is flickering blue, the middle LED is flickering blue, will you get the 2.7 volts. If the LED is not flickering blue, that means the 2.7 volts needed for the board enablement will not be there. Next, you can see a pin called GDRV. This GDRV pin is called the gate drive pin. So this gate drive pin is going into this MOSFET. It will turn on and turn off this MOSFET. And why is this required? This is basically the workhorse of this IC, which means the primary purpose of this IC is to produce a high voltage. So you give in 12 volt inside here and you get out 60 volt outside here. So how do you do that? Basically, it uses a very simple principle of physics. You can see an inductor here, this 2.2 22 microhenry inductor here. So when you know by high school physics that if you turn on and turn off an inductor rapidly, what will happen is due to the collapse, to oppose the collapsing, building up and collapsing field, the inductor will produce a very high voltage, and that basically is the principle. So that is how you are getting the boosted up voltage. You are getting 12 volt here, 60 volt output here. So this MOSFET is basically, what happens is you are switching on and switching off using this GDRV pin. This MOSFET will be on and off very fast at very high rate. So that the high voltage produced will get accumulated into this capacitor here, and that's why the 60 volt output will be produced. So how do you calculate the output to be 60 volt? Why not 50 volt? Why not 40 volt? So the design principle is basically the voltage output is proportional to the frequency of the switching of MOSFET. So if you switch on and switch off the MOSFET faster, you will get higher voltage. If you switch on and switch off the MOSFET slower, you will get lower voltage. So now the voltage which is produced here is basically an AC voltage, which is not very useful for driving LEDs. We require a DC voltage. That is why you require a rectifier here. You can see a rectifier diode here, and you can see a capacitor filter here. This is a capacitor filter, rectifier diode. But you see a small change in the rectifier diode. It is not like normal diode. You can see a small curved line on the top and the bottom portion, a right angle line, and this is a special diode, and it is called a Schottky diode. Now Schottky diode, it works at high frequency. As I told you, this MOSFET will switch on and switch off at very high frequency. So the ordinary diodes which you use will not work at such high frequency. That is why, and the drop across the diode also will be very less in case of a Schottky diode. So basically this will rectify it, and you will get a pure DC voltage here, and that DC voltage will be filtered by this capacitor, and 60 volt is available. And this 60 volt is nothing but what is going into the backlight LED. So all your backlight LEDs are getting fed from this 60 volt. Now you know how beautifully this 12 volt is getting converted into 60 volts. Beautiful principle of physics of switching the inductor at a very high rate, and that is what is called a switching mode power supply. You must have heard the term SMPS, switch mode power supply. So this is what is basically switch mode power supply. It is this is the practical circuit which I have shown you. So people might be saying that your TV or your air conditioner or whatever has got an SMPS. This is the SMPS. This particular configuration in SMPS is voltage boosting. You can also have a buck configuration, like I told you how we converted the 12 volt to 5 volt earlier in the board. That is the buck configuration. This is the boost configuration. Moving back to my LEDs, you can see the as I told you, the high voltage output 60 volt is driving all these LEDs, and it is connected to the anode of the LED. The cathode is connected to this particular pin. The one string is connected to IFB1, second to IFB2, so on. So we have this IC is capable of driving 8 strings of LEDs, having many LEDs in one string. So but here in my panel I am not using all the 8 strings, I am only using 4 strings. Now this IFB is also very special. This pin is also very special in that normally what will you expect? You are having voltage here at the outside, and here it should be ground, then only current will flow. Current always flows from higher potential to lower potential. So to glow the LED, you have a high voltage here, it goes through this LED and sinks here. These are all called the sink ports. But there is one small issue. Suppose I want to dim my LEDs. If my IFB 1, 2, 3 etc. are all kept at 0 volts, I will not be able to dim the LEDs. That is why this IFB has a very peculiar behavior. It will switch on and off, on and off, on and off at a very high rate. I will show you the graph and then it will be clear. So you see here, the moment the enable pin is on, the enable pin is on, the IFB voltages will start oscillating. Rather than staying at one level, it just goes on and off, on and off, on and off. Now this can be used for dimming. You will ask me how it can be used for dimming. Just increase the pulse width. If you increase the pulse width of the on and off signals, the LEDs will dim. So finally, to conclude, the basic idea was to explain all the functions of the various regulators and the backlight controller. So just because of this backlight controller internal LDO, that 5 volt VDD, because it is not there, this particular piece of equipment is totally gone. It's waste. So if we can find this IC, we can replace it. Even then, replacing is a tough job, because you see these pins are very closely spaced. I have a hot air setup with me, but even if I use a hot air setup, I can remove the IC, but I'm not very sure if I put a new IC, will it get shorted out or not, because the pins are so close. And other considerations are also there. You should have the proper temperature etc. to remove and resolder it back. The pitch is too fine, and can't do much about this. Even I searched online for this replacement, I could not I could find it, but I don't know. I will see. So here is the block diagram of this IC. This is the VDD which I was saying, the 5 volt LDO. This 5 volt goes into the main functions of this IC. Just see here, VDD is coming for the driver, for the gate drive. So once the gate drive is not there, the MOSFET will not fire. The inductor will not turn on and off and produce the high voltage required for the backlight. So that is about it. Thank you so much. It was nice making this video.